So for this little video here, I'm going to go over how to do a change of phase type problem. Sometimes we call them a heating curve or a cooling curve, depending on if you're heating or cooling your substance, whatever the case might be. There is there is some math involved. It's not difficult math. It does get to just be a little bit monotonous because a lot of times you have to set up several small problems to try this big problem. So let's look at an example. So this is a common example of how a problem like this might be expressed. How much heat is required to heat 45 grams of ice at -5 degrees C to 115 degrees C? Now, what I find helps me a lot is to be able to draw a heat curve so I can visualize this. Now, if you remember a heat curve, so we've got heat added, and then over here we have temperature. A lot of times I won't draw the axes on there, but you're going to end up starting off and it's going to go back and forth like this. And so what I'm going to do is I'm going to label these A, B, C, D, and E to show the different parts. Now A is when we're heating up ice. We're just heating up ice. Now, because we have something as we're adding heat, we see an increase in the temperature. The basic equation that you're going to use is Q equals ms delta T. So this is what we saw back in Chem 1. The only problem is that this S isn't the one that we're most familiar with. The S for whenever it is a solid is going to be 2.1 joules per gram degrees C. But you're going to have your mass, you're going to have your delta T. The next thing is B. So B is this section right here, and this is where we're changing the ice and we're changing it to liquid water. Now on this one, because this is a phase change, sometimes we call this latent heat. The Q that we have is going to be the mass times the delta H. And the delta H is going to depend on what phase that you're in. In this case, because we're going from a solid to a liquid for water, it does also depend on what your substance is. This is a plus minus 334 joules per gram. And whether it's plus or minus depends on if it's heating, where we're adding heat, or if it's cooling down, where we're actually releasing heat. Yeah, it's weird to think that if something freezes, it releases heat, but that's the way it is. Now the next section is we're going to heat the water. And when we heat water, we use the equation Q equals ms delta T. This S right here is 4.184 joules per gram degree C. Then we're going to change the water into steam or vapor. So again, we have some latent heat here or hidden heat. And so it's going to be the mass times the delta H of, sometimes I'll put a V down here for vaporization. The other H would be an F for fusion. I know fusion's the same thing as freezing or melting. They call it fusion. This particular delta H, again, for water is going to be plus minus, depending on which way you're going, 2,260 joules per gram. And then the last thing I have, that last little section, is where we are heating up steam, or we're heating the vapor. And so we go back to that Q equals ms delta T. But in this case, that S is going to be 1.9 joules per gram degree C. So we actually have 5 different problems that we're going to find, and then we add them all together at the very end. Again, each problem isn't hard. It's just, it gets to be a little bit monotonous in trying to keep everything straight. So what I'm going to do is I'm going to break it down for each part, and we'll look at how to do that little part. So let's try that. just going to draw a small diagram just to help me remember. And I'm going to be working on part A for this first part. So all I'm trying to do is I'm going to heat ice, heat. Well, it would help if I could actually write right. Right? Yeah. We're going to heat ice. And then we have to be able to look at that change in temperature that's actually going to occur. Now, for ice, for water, which is what this particular whole example looks like, we know that water is going to start to melt at 0 degrees C, and then it's going to evaporate at 100 degrees C. So if you're ever doing something that's not water, you'll have to know what that boiling point and that freezing point is for that substance. So here we're going to heat ice. Well, I know that the ice is going to start at -5 and it's going to go up to the melting point, which is 0. So I'm actually going to heat this ice for 5 degrees C. So from -5 up to 0. Now, because I'm heating ice, I'm heating a substance, and we're seeing a change in temperature, we're going to use the basic equation ms delta T. My mass is 45 grams. Now, that 45 grams is going to remain the same throughout all the problems. I'm going to take it and multiply it by the S. Now remember, your S depends on your specific heat capacity, does depend on the phase it's in. For ice, I'm going to use the number 2.1 joules per gram degrees C. And then we're going to multiply it by that change in temperature, which in this case is 5 degrees C. Now, I did this a few minutes ago. Assuming my calculations were correct, I typed it into my cell phone. Double check my math because it'd be awful embarrassing if I got these numbers wrong. I ended up with 472.5 joules. Now, this is an example of where we have to add the heat to make it heat up. It's not being done spontaneously, so this would be a positive number. Well, I still have some room on this slide, so let's go ahead and do the next part. Let me change colors though. Let's change to a blue. So the next part I'm going to do is this letter B. And what letter B is going to look at is I'm going to change the ice to water. Now here we have a phase change, and whenever we deal with phase changes, that Q equals M delta H, where we have the mass, and then we have the enthalpy of, of, um, of fusion for this particular example. So sometimes you'll see they'll actually write a little F after that because here we're trying to melt that substance. So we're freezing or melting. It's the same delta H. It's just the only difference is if it's positive or negative. So on this one, we have our 45 grams. Now, if you go back to the previous slide, you'll find out that that delta H of fusion is 334 joules per gram. So I would take those basic S's and delta H's and make those really obvious as you're working out these problems. Now this one, we just multiply these two numbers together. Notice there's no change in temperature for this one. And what we find is that the amount of energy required to change that 45 grams of ice to a liquid water is 15,030 joules. That's a lot of energy. That's a lot more energy than that 472 joules it took to heat up that ice. So that latent heat, that hidden heat, you'll find that there's a lot of energy that goes into changing phases. So that talks about the types of intermolecular forces you might have. All right, we still have room, so let's do the next one. Let's look at letter C. Letter C is whenever we have the water and we're going to heat the liquid water. Heat liquid water. Now, because we're going to see a change in temperature, we're going to use that Q equals ms delta T. On this one, our mass, still 45 grams. Our S, in this case, because we're looking at liquid, the S is 4.184 joules per gram degree C. Sometimes they forget to include that 4. Sometimes I forget to put the 4 on there, but I think I did put it on this time. And then we have our change in temperature. So if we go back to that graph, we're going from the freezing point all the way up to the boiling point because we're actually going to go past that boiling point in the problem. So for it, while it's a liquid, we're going to have 100 degrees that we're heating that up. Now, when we multiply these all together, turns out this should give you about 18,828. Can't write my twos today either. 28 joules. All right, so what do we do next? We've heated the ice. We've changed ice to water. We've heated the water. So now we have to change it to a vapor. So the next part is going to be letter D here. Letter D is going to be our evaporation. So we're going to take our liquid water, and we're going to change it to steam or a vapor. Vapor is probably a little bit better word to use right there. Now, because this is a phase change, which the equations are we using? Yep, that Q equals M delta H. We still have 45 grams. That has not changed. The delta H is the enthalpy of vaporization. Sometimes I'll have a little V written after that. For the vaporization amount, this one, remember, it takes a lot of energy whenever you change things to a gas phase because you more or less have to get rid of all the intermolecular forces that are between two molecules. So in this particular case, that amounts 2,260 joules per gram. So it's a really, really large amount. And so we find when we multiply those together, we have 101,700 joules. Now there's one more little phase change that we have to do. We have to go from that vapor and we have to start heating up the vapor. So let's look at that one little last part that we have left. So this is going to be letter E, and this is going to be this last little part right here, where we're going to take that vapor and we're going to start heating it up. So we're going to heat vapor. The basic equation we have, Q equals ms delta T. So there's only two equations that we're using. The S's are different, the delta H's are different, but you'll go back and forth between those two equations. The mass, 45 grams. The S, now in this case, we're looking at the vapor, and the vapor has a specific heat capacity of 1.9 joules per gram degree C. And all of those values have been given to you on that worksheet. So I want you to use the same values that we've used in this particular problem. Now, other books or other examples you might have instead of joules, you might see kilojoules or calories. You can do moles instead of grams. But I believe on that worksheet, I have it all in the units that you see in front of you right now. Now, in this case, we need to look at that change in temperature. Now, remember, our sample didn't turn to a vapor until it was at 100 degrees. So we need to look to see what happens from 100 degrees to 115 degrees. So my delta T for this part is just 15 degrees C. So we multiply this part together, we get 1,282.5 joules. All right, so we've done all of the individual steps. Let's see what we need to do next. All right, now we're to that last step where again we had this wonderful little heating curve. We've identified how much each of these little sections was, and now we just have to add them all together. So we're going to look at section A. A was going from ice at -5 to 0 degrees C, and we found out that it took 472.5 joules to heat it up. And then what we did, letter B right here, is we changed ice to a liquid, and we found out it took 15,030 joules to be able to help with that. So that's B, this is A, here's C. The next thing we did is we started to heat that liquid, and that took 18,828 joules. Then we took that liquid and we changed it to a gas or a vapor. So that was 0 to 100 degrees. And then we're going to heat the vapor. I'm sorry, I messed that part up. Oh my goodness, we didn't heat the vapor there. What did we do? We changed it to a vapor. We took the liquid, changed to a vapor. And we found out that takes a heck of a lot of energy. That was 101,700 joules. The last thing we did, this last little section here, is we heated that vapor from 100 to 115 degrees C, and we find out that it takes 1,282.5 joules. And then what we're going to do is we're just going to add those all together. Now again, assuming I did my math correctly, that should be 137,313.0 joules. So this would be your final answer. It takes a lot of energy to heat just 45 grams of water with that much of a temperature difference in going through the two phases. So on the problems that you have, you won't necessarily have to do all these steps. If you start off with liquid water and you're heating it to steam, well, you don't have to do the first two steps that we did. You don't have to deal with it as a solid form. Or you might be able to stop earlier depending on the problem that you have. So I highly recommend drawing the little heating curve. For me, it really helps identify the different sections and what I'm doing with it. And then just break it down. Keep it nice and simple for each step. And then you're going to add them all together at the end. So good luck. If you have problems, just let me know. See you later.